So safety should be accessible to everyone. It shouldn't be a luxury thing. It should be something that is the basic for every vehicle. Welcome back to yet another episode of Autonomous Vehicle Safety and Security Podcast. Today we have an amazing guest, Leaf Jiang. He is a 100% MIT product. He did his bachelor's, master's, and PhD from MIT in electrical engineering and computer science. And then he did his internship at Bell Labs. After his internship, he came back to MIT Lincoln Lab, where he did 12 years of research with LiDAR. And before forming Nodar in 2018, he was involved with an engineering consulting company, and in 2018, he founded a company called Nodar. So, Leaf, welcome, and welcome to our podcast.
Thank you. So excited to be here.
You have an amazing career path. I mean, nothing gets better than that. So why don't you tell us a little bit about how did it all get started?
Well, I would have to say that my father was a big influence in my life. He was an engineer as well. Came to this country from China, and eventually had a test equipment place where he serviced test equipment. So I grew up in a laboratory. I literally grew up in a shop in New York on 38th Street. It was an industrial area. In the front of the house was a whole bunch of oscilloscopes and spectrum analyzers and all the equipment he used for repairing industrial recording equipment at the time. And the family lived in the back. So at a very young age, I was just a toddler walking around like scopes and resistors and those kind of things. So it was just part of my DNA since the beginning. I was an easy kid. My dad said, study engineering, go to school, and focus on your studies. I'm like, all right, Dad, sounds good. I was just excited about it. It was just something that just grew up into. So like the blacksmith and the blacksmith's son sort of a thing.
They must be very proud of you, right? So how did the entrepreneurship come into play? Because you had an amazing career, you were doing great research, and entrepreneurship is a whole different ballgame, right?
Yeah. So funny thing is, when I was an intern at Bell Labs, my advisor, Norm Whitaker, which by the way went off to DARPA, did the DARPA Grand Challenge. So small world. He told me, he was at Bell Labs and he left for DARPA at the time. And he said, when you're my age, you'll understand. And he was, about 40, I'm guessing. And I was like, okay, that's fine. I was like a young, undergraduate at that time. And I thought I was going to be in academia forever. So I went to MIT. I love doing research. I love discovering new things. It just was so exciting to find new stuff. So I was at Lincoln Labs, this very academic oriented place, publishing papers, figuring out new ways to measure things. LiDARs going out to megameters, doing these things from aircraft, doing these things from vibrating platforms, which is hard to do with laser vibrometry. And eventually you get to an age and you're like, okay, this is great. Like the research is something that's might be relevant 20, 30, 40, 50 years from now. But then you get to realize, when you're in your 40s, 40 years from now, you're probably not going to be alive to see it. So at that point, you're like, well, I'd love to see the product of my work, right? So at that point, it was like, well, I want to see something happening sooner than that. So that's where entrepreneur fits in nicely, right? You're doing something a little bit more immediate, and you're trying to apply these advanced principles to make a difference in people's lives. So I just happened to be lucky. I was in a field that happened to be needed at the time before. And when I started in 2002 with LiDAR, no one really heard of it. No one really knew what that was. And nowadays you even have rap songs about LiDAR, which is kind of funny. So it was the right place in the right time, and also a place in my life where I wanted to start seeing some impact. So that's how it all came together.
Amazing, Leaf. What I'm really excited about is several things. In between the consulting company, engineering consulting company, this is super, super exciting. Why did you found a consulting company, engineering consulting? What was the purpose of that? And how long did you run that company?
Yeah, so that was about 3 years from 2015 to 2018.
Mhm.
So I had been following sort of the self-driving car thing for a while and LiDAR for a while, but it wasn't prime time for me to jump into that yet. So I was more interested in um, just making more immediate impact. So I started a consulting company, probably in the worst way possible. There's like a competition-based crowdsourced platform called Incentive, where they take Fortune 500's toughest questions. They're too embarrassed to sort of say that they have these problems, so they go through a third party, in this case, Incentive, to crowdsource it. So they put these problems out. Usually they get anywhere from 200 to 400 submissions to solve these problems. And from those, I grew my engineering company. So I won 4 or 5 of these competitions. The type of work spanned everything from low noise transimpedance amplifiers to probably one of my more successful projects was a handheld spectrometer for detecting counterfeit money, counterfeit products, providing the lowest false alarm rate in the world. So I built a $50 device for this company, and they did very well with it. And from that, I learned, well, maybe consulting's not the right place to build innovative products. You're probably better off actually doing one. So that was sort of the realization and genesis of Nodar in 2018.
Fantastic. So, how did you start? What is the first thing when you thought about founding the company? What did you do? What were the steps?
What were the steps? So the start was a long start. It was something I've been working on for a long time. LiDAR systems, I've been following the space for, I would say, 12 years. So I wouldn't say it actually started back then, but the inkling started a while ago. In 2018, it actually started in 2017, summer of 2017. I remember one summer, I'm like, man, these cars are never going to get into mass production the way they're going about it, spending, 12 years working on LiDAR systems, knowing like the cost reliability was going to be a problem back then. But so there was just this knowledge of, okay, there's a better way to mass produce these things and get 3D information. Our company works on software approaches of taking multiple cameras and synthesizing 3D point clouds. And that would be a more mass producible approach to getting high resolution 3D on every car. So the initial ideas were in 2017, and there's always tons of pivots. So when you look at sort of the history of where our patents were and what was done, you'll see that we actually started out as more of like a hardware software company. We had patents around optical filters, patents around system stuff. But at the end of the day, as with a lot of researchers, you're thinking 10 or 20 steps ahead. You only need to take the first 2 or 3, right? So we realized quickly that the software was the key part in starting all of it. But anyway, who was involved? So it was there's a really neat venture ecosystem around MIT. Not surprisingly, a lot of universities have this, which is super important. At MIT, they call it, one of the things is called Venture Mentoring Service, VMS, and they pair you with folks that are interested in helping young entrepreneurs sort of get going, right? So the early committee consisted of a number of retired veterans that were either in automotive or did engineering at large consulting companies. And we had meetings and talked about the idea, the go-to-market, for several months before even incorporating. And it was actually through that organization where they had an event where they were demoing all the different VMS ventures, where I met sort of the first cash that went in. So that was the Cherry Stone Angel Group. So this angel group came to the demo. They saw my little apparatus on this table, measuring 3D images of the ceiling and different things in the exhibition hall. And they were the first money in. So the angel group came in and wrote in a convertible note. That process was a long, painful process. Nothing's ever easy in entrepreneurship. But it was the first validation of, well, this is an interesting idea, and people are actually willing to open their pocketbooks to it, which kind of kickstarted the effort. And from there, shut down the consulting company a little while before, and went into it full time. So that was the beginning of it. Early days.
Love that. Love that. So now I'll come back to the entrepreneurship part, the business part in a bit. For now, let's pause here with a entrepreneurship journey, and let's talk about the technology. What is Nodar, and how does that work?
Yeah, what is Nodar? So we're a software company. We build software that takes any two cameras and create point clouds out of them. So it's basically wide baseline stereo vision. It's a very reliable technique of measuring distance to every pixel by triangulation, basically. So by having a wider baseline or wider distance between the cameras, the farther you can see. And so in the past, it's been very hard to pull the cameras apart because they tend to jiggle, and you only need to jiggle them about a hundredth of a degree for the measurement to fall apart. So it turns out to be a very difficult calibration problem that we solved. And this allows us to really take advantage of the size of the vehicle to see very far ahead. So we've built 2-meter systems on cars, 3-meter systems on trucks. These are probably the most unfriendly environments to put sensors. They vibrate, the temperature's all over the place, there's a lot of shock. And even through all of that, our calibration software stays intact so that we can actually do the triangulation measurement safely and accurately. And the whole thing is about safety in cars, right? It's about getting a safe measurement, and it needs to be fundamental to the actual measurement you're doing. So the less interpretation there is, the better. So that's why people love LiDAR, because it's time of flight. You just measure how long a photon goes out and comes back, and it's very hard to fool that. You're measuring a physical quantity, right? Like a tape measure. And triangulation is similar to that in the sense that you're measuring angles. So you measure the angle of the object between the two cameras, and that gives you the distance. This is markedly different than an AI approach, I would say, in the sense that you're not deducing the distance based on information that you're not sure about. So case in point, there's some new papers coming out on invisibility cloaks. People are printing t-shirts with these crazy patterns, and they're wearing them, and these face detectors, they just suddenly they're invisible. The face detectors don't work on them. So they take advantage of these black boxes in these clever ways that are fundamentally, if you were building a system, that would be terrible if you had a car trying to do some sort of person detection. Someone puts on this shirt and suddenly it doesn't detect them, right? So fundamental is, safe measurements of distance. And the most important thing that we learned from the DARPA Grand Challenge days in 2004 to 2007 was that the high resolution 3D is really the measurement that opened up and enabled this whole idea of getting to higher levels of ADAS or to a point where we have unsupervised driving, because it just simplifies the problem enough to do the computation on the lower power that a car has.
Gotcha. So that's a lot of information for the audience. Let's just try and get into all of these things one at a time. So point cloud triangulation, like you said. So basically what you're doing is the same thing a LiDAR would do, but you're not using a LiDAR. A LiDAR would give me a point cloud as well, right? So you're not using a LiDAR. And what you're saying is the measurement is better than a LiDAR. And there are certain cases, like, you gave some examples where people will be probably invisible. In certain cases, when LiDAR will not work, your technology will work. In a nutshell, it's a summary of what you just said. Is that correct, or?
Yeah, sorry, I brought in too much, but yeah, that's more or less correct. So how does our system compare to LiDAR is a great one. Well, first, how does the measurement work? Why don't we go over that? So yeah, stereo vision is measuring distance, much like human eyes, right? Left, right eyes, and you're looking at an image. And if you put your thumb in front of you and you kind of blink the left and right eye, you'll see your thumb move left and right. And that displacement or disparity is a measure of distance. So it's a
Hmm.
direct translation of shift to distance. The closer it is, the bigger the shift. As I move my thumb farther away, I notice that that shift gets smaller as I blink between both eyes or both cameras. And so smaller displacements or smaller disparities means that the object's far away. So that's what I mean by direct measurement, right? That you can just measure that shift between the two images and you get the distance. Um, Now, how does it compare against LiDAR? There's a lot of things. The two big things that the automakers really care about is our cost, right? Obviously, so cameras versus LiDAR. There's a big difference there, and reliability. So these things need to last, for example, 15 years. And it's very hard for a mechanical LiDAR to last that long. As far as I know, I don't think that any have gone that far. They're typically spec'd out to 7,000 hours. Um, and so those are the big things. But more importantly, is like, where is this going to trend, right? Are there any physical limitations? And I think when you look at LiDARs, there's two important physical limitations that no matter how much money or how much, you do, you can't get around the physics. Number one is the speed of light. So the ability to the measurement itself, you're waiting for a photon to hit something and come back. The speed of light is 3 times 10 to the 8 meters per second. So if something's at 150 meters, I need to wait about a microsecond for the light to come back. And that sounds pretty fast. Now, a microsecond to hit a target and come back. But if you have to repeat this 5 million times, like our 5 million or 5 megapixel arrays, well, 5 million times a microsecond is 5 seconds. So that becomes quite significant. And 5 seconds, it turns out to be the time it takes for highway driving 65 miles per hour to cover 150 meters. So there's no way to scan the road fast enough before you hit something, it turns out. There are ways to get around it, which people do by using more channels, so more than one beam of light. So you can go up to, they have 128 channels, and it makes it a bit faster, but it's a very expensive way of scaling. So the big problem is speed of light there. And then the second is maximum permissible exposure. So there's only so much laser power you can send out before it becomes not unsafe for human vision, for humans' eyes. And that is, we're kind of at that limit right now. So you can't expect these lasers to increase in power that much more before you're worried about maximum permissible exposure. So there's this upper limit, and we typically see the fancier LiDARs, like the 1550 nanometer LiDARs you hear about, maybe getting a few points at 150 meters. But beyond 150 meters, they're kind of not very reliable. They don't really return too much. And so there's really a couple advantages of going camera based, right? One is the range. So we can see, 1,000 meters, no problem. It's the resolution. So typical automotive cameras are like 5 or 8 megapixels, so we can get that in a single snapshot. So things finding like small objects in a big scene, needle in the haystack kind of things, that's something that we can do well, which happens in driving quite a lot, right? A little obstacle like a cinder block in the road. How do you find that? You can't wait for a scanning system to find it. You have to find that very quickly. And so those are two sort of important points on the sort of performance that you can do with a camera. And the common complaints of nighttime or weather, what we're finding is that actually there's a paper published that they actually do better in poor weather than LiDAR systems. And nighttime is becoming less of an issue with more advanced near IR and regular headlights. And lower noise CMOS arrays, they're basically photon counting cameras with 2 to 3 electron readout noise. So all these things coming together with now sort of the cheaper sort of compute that's happening all around with automotive SoCs are making it a very, very compelling case to get into mass production.
Fantastic. So you talked about two main limitations of LiDAR, which you don't have when you're using cameras. You also mentioned a bit what actually would have been my follow-up question is the weather. Yeah, I mean, nighttime, I like the explanation you've given. How about bad weather? How does that work in different weather conditions?
Yeah, so that's a great question. Typically, we do tests in rain, but there's also snow. There's the bug test. So there's two real main effects of weather on a sensor, right? For optical sensors. One is stuff that's occluding your aperture, so junk that's on your lens. And then there's the distributed scattering effect of like having these sort of distributed scatter in the atmosphere.
Gotcha.
So we'll talk about one at a time. So on the sort of stuff on the lens, so lens, covered in raindrops, how does that affect things? It turns out that if you build your optics right, it just reduces the contrast slightly. And we've done this quite a lot. We've had lenses coated in droplets with only with slight contrast reduction. The reason for that is you build the focus that goes beyond sort of the aperture, right? It's the same reason that a motorcyclist can drive in the rain. They're not focused on their head, on the visor. They're focused beyond that. So it's pretty straightforward to have still be able to measure things at long ranges with stuff on the visor, stuff on the lens, because it just is a slight contrast degradation. It does degrade the estimates, but it's way less than what people think. Most folks think of like dash cams and fisheye lenses, which have super short focal lengths, which are more susceptible to like stuff on the lens. But when you design something that's supposed to look out a little farther ahead, just like a motorcyclist kind of looking out past his visor, these degradations are actually very small. So we've done a ton of testing with OEMs, not just with raindrops, but with dust, with dead bugs smushed onto the lens, all sorts of things. And it actually doesn't affect the performance as much as one would think. When you look at LiDAR systems, you tend to get a lot of backscatter from that, which could be an issue depending on how you built your LiDAR system. But for optical systems, because it's an intensity measurement and because the contrast reduction degrades gracefully, it tends not to be an issue. The second effect of weather, okay, distributed scatterers, right? So I've got raindrops in this column of light or column of my field of view, and for that, typically the way that a camera measures things, it's an intensity measurement, right? So you're comparing the shift of two things that have some sort of intensity profile to it. So unless that distributed scatterer is enough to reduce that or change it in some significant way, it turns out that the distributed scatterers are not that effective. So this is the same as saying, when you go out in a rainy day, at what point can you not see things? It's actually pretty extreme, right? Whiteout conditions or rain levels where you actually can't see something at 50 meters is super rare. And because we're measuring the biggest intensity, these distributed scatterers are typically not significant. So there's a graceful degradation. And so you can go from light rain, medium rain to heavy rain without much of a degradation. There's folks that have done this research and published it in the past. We can quote some of those papers. But it's fundamentally because it's an intensity measurement, as opposed to if you have a distributed scatterer with an active system, well, you're always getting photons back from that distributed cloud. And so especially if it's a photon counting system, it might trip your detector before it sees the car behind the sort of rain cloud or snow cloud or whatnot. So I would say as long as you can see things, like make features out with your eyes, we're in good shape. If it's whiteout conditions, well, we don't have X-ray vision, right? So we can't see through like pure whiteout conditions. But we do know when those occur. So we do have something in our software that says on a pixel by pixel basis, what's the confidence of that estimate? And if there are A, not enough photons, or B, just no features to lock on, meaning it's like a fog or whatever, then we'll just say, well, the sensor doesn't know. So that's actually sometimes more important than being able to work in every condition, which no sensor can. Just knowing when your sensor is not giving you the top quality data is super important. And that's part of what we do, is present what we call a confidence map for every pixel on every frame.
Love that, love that. You also mentioned that it's a not AI approach, right? I mean, can you elaborate that a little bit? Because, typically what I've seen in this camera-based approaches when you're trying to detect an object, classify an object, it is there like the corner cases. There are so many corner cases that can happen that makes the system so complex. So what I was intrigued when you said this is not AI-based system, so there is nothing. You're not actually making any prediction or extrapolation. So can you talk a little more about that?
Yeah, so I mean, AI makes sense for certain things, but it doesn't make sense when fundamentally the quantity is not learnable. And
Mm-hmm.
so if I have a monocular camera system and I'm trying to determine the distance to an object just from an image, it's what in publications they call an ill-posed problem. Right? I just know where things are in angle space, and from that I have to estimate where things are in depth. But there's so many known edge cases and problems with it. It just tends not to be a safe way of doing mono depth, I guess is the name of it. Um, the problem with that is when we say ill-posed is there's just several ways to have the same answer. So there's no way to learn it right. Like, what's the difference between like an adult and a child? Well, factor of 2 in height, but if I'm build a detector and I'm counting the number of pixels, well, I could be off by a factor of 2 in range. That's just a very simple way. There's much more complicated ways of failing in these types of systems. There's no way to differentiate a movie from a real scene, for example, right? They have the same information. There's no way to differentiate someone projecting something on the ground or paint lines that just happen to be wrong, like the perspective's off or something. A car that's half the width. I mean, I just went by one the other day. I'm like, wow, that might confuse an AI system if you run into some cases that are kind of weird. Or you hear about blue cones in Japan versus orange cones here. Like, you don't know. I mean, the problem is the testing involved is so costly to do these to validate these systems that not only is it difficult to get right and impossible in some cases, but just testing it over and over when you make changes is a very expensive, slow way of doing things. Anyway, so I prefer and I think our philosophy here is, we want to get as close to a real physical measurement as possible for something as basic as range, right? And from that, you could layer on your AI. So once you have like your 3D point clouds and you're like, all right, I've segmented it. Here are the boxes. Let me see if I can apply a classifier to that box so that, if there's something sticking above the ground, what is it? That's a perfect place to put in an AI saying, oh, well, that looks like a person, or that looks like an animal or a car. But you'll know that there's something there sticking above the ground. So giving meaning to the points is perhaps a better place to put an AI than to get the actual physical measurement of distance.
Talk a little bit about safety because, you're talking about range, simple range, right? So as something as basic as range, you can do it as accurately as possible without AI, and you want to do that without AI. Now, have you also in your company looked at those safety norms that exist in the classic automotive industry like ISO 26262, and more interestingly, the extended version, SOTIF, Safety of Intended Functionality? Have you looked at how does that work together with your solution?
Yeah, so we're super serious about that. We're ISO functionally safety qualifying our software 26262 through an external well-known consultancy that does this kind of stuff. And we're doing it for different parts of our stack as well. We're going through that exercise right now. We're doing safety out of context because there's several applications to it. And in terms of when you go through these sort of exercises, they all boil down to what fundamentally are you doing, right? So I mean, part of the whole standard is like just setting up your processes correctly, but what's kind of down deep in this? Like what is fundamentally safe about your product? And I think, so I did touch upon one aspect is like not just reporting distance, but like how well do you know that distance, I think is an important aspect. So you know how to do the handovers. The second aspect is time or range, as you alluded to. So the sooner that I can detect something, the more time I have to make a decision or safely or smoothly change lanes or, on an object. So case in point, if I'm a truck traveling down a highway at 60, 65 miles per hour, I have to actually see small objects and large objects at long ranges. So if I have something hazardous like an overturned motorcycle at 200 meters or 300 meters, I need to know that pretty soon, because the worst thing to do is just to hit emergency brake at the last second and cause a pileup. But so one of the nice things about our sensor is that because it's camera based, we can see very far. We can pick up these objects. We've got the baseline to actually get the range to them. We can find the ground plane. We can see things as small as 15 centimeters sticking up above the ground surface. So we can pick up the motorcycle. We could pick up the downed motorcyclist, his helmet, traffic cones, small boxes, cinder blocks. Ripped tires, we've done it all, and even tires, right? Tires is an interesting one because they tend to be very black and very low reflectivity targets. So they actually come up pretty well in the cameras. So being able to see these things far away means that you have time to react, and it's about 5 seconds per 150 meters. So if I find something 450 meters out, that gives me 15 seconds to react, which is great, right? That's like the dream of any sort of control systems engineer, right? That's looking at this in Path Planner. Whereas if I were limited to say 150 meters for a LiDAR system, that might limit me to less than 5 seconds, right? So first I have to detect it, then I have to decide what to do, then I have to do my maneuver. That gets very, very scary when your timeline gets eaten up. So it's a very simple safety equation. The farther you can see, the safer your system.
Fantastic. So, there's this example that we always bring up in safety, that what is the time required for a person, a human, to hit the emergency brake when they see an obstacle? And it turns out, on an average, it's 1 second. So this is actually a long time. As long as your AI or your automated emergency brake or system can beat that number, I think we're talking about severely less injuries compared to a human-driven vehicle. And I think your technology seems like it's going to play a major role in autonomous vehicle. Now, how does the product actually look? Is it only software you're delivering to the OEMs, or is it like you have also those hardware cameras? What is your product? How does that look?
Yeah, so there's definitely a large stack that goes into autonomous vehicles, right? And everything from the sensors to the sort of first data products of building out the 3D point clouds to object lists, and you start tracking those objects, and then you have a path planner that decides what to do with that and behaviors around that. So we don't do the full stack. We're not an AV company. We do the software behind the cameras. We offer reference designs, but we're not in the business of selling cameras. There are other folks that do that well. Gotcha. And so we sell the software that takes the cameras and basically converts it into point clouds or object lists.
Got it. So basically, your solution is the software, and you're giving some guideline for the hardware as well.
That's right. So we like to play with any camera, right? Like from VGA to 20 megapixel, global shutter to rolling shutters, visible cameras to long wave IR cameras. Like we can do all of that, which is awesome. So we're very camera agnostic, and that in some sense has opened up the design space, because if you look at standard old school stereo camera options, you might have 5 or 10 options with very limited choices for cameras, fields of view, and everything. But now where you can use any camera, any wavelength, any place on a car, you have a huge design space for where you can put these things. And they don't just have to be horizontal on the roof. They could be in the headlights. They could be behind the windshield. They could be on the side of the car. Tesla's got some nice ways of putting them in sort of the body or in the door, if you've seen those. But you can imagine doubling up these cameras and getting full 360 coverage to be able to turn your camera into something that actually gets real 3D out of it.
Got it. So let's come back to the business aspect a little bit. Is your software stack in any series vehicle today?
Not yet, not today. We're not in any series vehicle today. It's this is a long, long journey, right, to get
It is.
into a various production vehicle. But we're past the innovation stage. We have quite a number of POCs and pilots.
Mhm.
So I would say we're in a stage where we're trying to get designed into the series production, right? And so that's currently where we are and where a lot of this is in terms of the technology. There's a few
Gotcha.
things that there's a few things that have to come together for this to sort of be mainstream. I think we're taking the view that cars will eventually be like your phone, right? It's like you've got the app store,
Totally.
centralized compute. We're not quite there yet. So right now, compute is compartmentalized. It's called edge compute, right? You have your mobile eyes behind the thing, but it does everything. The camera in and brake out, right? Like it's all computed there. Whereas I think that the the future, which is like Mercedes L3 platform and others, Tesla as well, have centralized compute, right? Where all the sensors go into the centralized compute, where it makes a decision on how to go. And that's important when you start doing sensor fusion or you want to have more upgradable path, but that's where we think that will have the greatest impact. I think the L2, L1 days are numbered. So we're designing for a roadmap that looks more like, something like an NVIDIA Orin in a car, right? That's running in a couple of these vehicles like the Volvos and stuff. And then we would be a software component that sits on that subscribes to these feeds and outputs something of quality. So I think that is here and coming in the next few years, and it'll be prime time for us to sort of uh, hit sort of the product at the right time.
It's mind-blowing, Leaf, what you just said, that it's going to be like an app store. This got to happen because now if I ever have a car and if I uh, want to use somebody else's even navigation system, it doesn't allow me. I'm tied to the OEM's navigation system. I'm tied to the OEM's apps, whatever that's the OEM's providing me. And we know that when you do not allow others to come into your app market, it can be a death sentence for the company. We have seen that. We've seen Nokia, right? So I have talked about it, and I really love the fact that you also mentioned the same thing. And we will see which company actually becomes the platform and what will be them. It is likely to be them. I mean, you mentioned two names, Daimler and Tesla are the ones who are in sort of in that direction. But I think it's an absolute essential for this entire technology to really the big bang to happen. This is going to be the big bang in autonomous vehicle if that happens. It's liberalization of software. Now, you going back to you said this is a long journey toward series production. I agree. I totally agree with you. We also help companies like yourself. I mean, we're right now helping another Silicon Valley based company to get through the automotive hurdle like ISO 26262, ASPICE, and now we have ISO 21144 for cybersecurity and all those. How has this been as a journey? I mean, you're still working on that. Can you tell a little bit about your experience toward that, with this automotive hurdle, like toward the series production? What are those, and how are you dealing with those?
Yeah. So I think there was a lot of discovery of where this technology would fit in best when we looked at sort of the fast market stuff. So you're looking at construction, agriculture, dump trucks, even, right? Like the smaller volume but more immediate. They needed more of the stack built up. Like you couldn't just come in with 3D vision software. You had to build up the entire stack to building, in one case, an arm that grabbed trash cans and put them in from soups to nuts. And so we decided not to become a trash services company, but focus more on larger companies. And it takes longer, but the volumes are higher. When you look in that market, you can break it up a bit. It's not all the same. So I would say the beachhead markets right now, if you look at it, are like L4 trucking. They're skipping L3. They just want to get to autonomy because there's a real financial benefit to that. They know exactly how much it costs per mile to run a truck. And it's a very simple equation. And given the lack of drivers, I guess, worldwide, it's really compelling to get to L4 quickly on say the long haul routes. That's where we have a nice advantage of being able to see stuff farther away than what current sensors can do. And so we're filling a nice gap in the sensors there. So that's a very fast way to go forward. And I think we're making very good progress in that sort of beachhead. In the car space, what you're seeing is sort of a retrenching and folks really focusing on L3 now, I think overall. With Mercedes, obviously, as I mentioned earlier, with their traffic jam assist, up to 60 kilometers per hour on the in a traffic jam, you can read a book now. I mean, people are sort of blown away that you can actually let the car drive, and if anything happens, it's Mercedes that's going to pay for everything, right? Like that's a big deal. And as far as I've heard, there's no problems, which is actually surprising, right? This is the first of like, there actually have been L3 like Honda, right, did this thing, but this is a bigger deployment here. And I think this is going to pave the way to greater things. Everyone's in chasing mode now. Like, oh, wow, so Mercedes done this, and you'll see a lot of the other OEMs, which I can't name, are chasing that. And we'll start seeing a lot more of these functions appearing. But the big difference is unsupervised driving, right? And so any ODD in which you do that is a big deal, whether it's a traffic jam or as you get faster, right? So if you look at sort of regulations in Europe, the UN regulation 157 has kind of opened up stuff in Europe, right? That's why we have the initial one that allowed this traffic jam assist, which got recently revised to go to 130 kilometers per hour, which is pretty cool. And in that, you'll see specifications for range and the assumptions for that. So for higher speeds, you need to see at least 150 meters ahead on a road with barriers. Once you take that barrier away, that becomes 300 meters because you have to see oncoming traffic. Or if you're in non-ideal conditions, it increases the range. So there's this ODD that can be opened up by simply seeing farther out. So you'll become more useful, like not just highways with barriers, not just highways with good weather, not just well-marked lanes. It'll be a larger set of roads that opens up to L3, which is going to be amazing. So I think, those are the immediate places where we see our technology going into series production. And I think that eventually it'll be we're finding out that L3 is not getting skipped. Remember a couple of years ago, people were like, oh, L3 is going to get skipped. We're going to go straight to L4. Well, that's not what's happening. It's L3 and it's a bit more, than L4 afterwards. So maybe the robotaxi next. And that's just what's happening. And as for L1 and L2, I feel like they're stuck in a non-centralized compute world. And I think you need to get to centralized compute, and then you could start replacing some of those functions. So there's a number of folks that are looking at using existing cameras on the vehicle, which do have overlapping views to get 3D information out of, which is also another aspect for close-in applications.
Got it. So, and you painted the picture really, really well, the roadmap, so to say, toward L4. I completely agree with you, and I was very much against L3, which I still am, but it's like, the industry will have to show some kind of progress, right? And L3 is a very, very tempting in between before we go to L4. And there's certainly some benefits to it. You know, if Mercedes, like the example you gave, they take the liability of paying for it, of course people are going to love it. Now, within this process, like, you know, when you're actually going to a traditional OEM, and you are a software company, right? You know, automotive have a very traditional way of doing things, which takes a lot of time. Like the path is long. As a software company, what are the difficulties that you're facing that, okay, in order to get to a series production, these are the, like, if you have to name some of those difficulties that you're facing? Because let's put it this way. Traditional automakers, unlike Tesla, they still do not think that they're software companies. They're actually building software on wheels. They're app companies on wheels. Tesla is the first one they thought like this, and what I see is traditional OEMs are trying to get there. The only problem is they're trying to become a software company within an ecosystem that is not designed for that. So I see a lot of hurdle. And how about you? I mean, what's your experience when you go to them? What are the hurdles that you see? What are the difficulties?
Where they love it when they see our stuff. They're like, oh, good, a startup that doesn't want to choke my supply chain by selling us one-of-a-kind cameras, right? Like, there's no way you can be a sole source. I mean, that's just, you'll never be in a vehicle unless there's more than two bidders for an object, for a piece of hardware. I would maybe disagree a little bit. I would say that maybe behind the scenes, all the OEMs want to be software companies and not metal stamping companies. There's very few profit margin in, like, injection molding and stamping metal. I mean,
they want to be software companies, but
yeah, it's hard.
It's like, it's hard to come out of that ecosystem and be a software company, as agile as Tesla.
Yeah, well, this is the opportunity, right? We're an agile software company, and they're trying to be agile software companies. So VW is, they spun out Cariad, which is a big deal. Right? It's a big deal of, like, hey, we want to do software big time. And I think that if you look to the future and you're saying, okay, the future is EV, right? If it's electric vehicle, what's the difference? I mean, everyone is selling batteries with wheels in some sense. Like, there's no differentiator in some naively, right? It's like, to the consumer, this is just a skateboard and battery with wheels. So what is really different from manufacturer A to manufacturer B? Well, it's going to be the software, right? This car drives itself reliably and it won't kill me. And this one, I still need to drive this one or whatever. I mean, the software feature is going to become more of a differentiator like you've never seen before, versus in the past, it was a little bit more hardware driven. Like, oh, this one had this particular hardware feature. So I think especially in this new EV world, when companies need to differentiate their product from just not being yet another battery with wheels, I think they're going to look to, software components to give that differentiation.
Totally. It's already today, they make most of their money with software. I mean, hardware is like just a commodity. Yeah. So with that, let's get back to the the business aspect a little bit. So where are you? Are you raising any series right now? How many series have you raised? What's your plan? And who's backing you up actually right now?
Yeah. So we just raised our Series A this year. We raised $12 million from NEA as the lead investor. They're a pretty well-known investor, and also supported by Rhapsody Venture Partners for our Series C, and they were also in the A. And as I mentioned earlier, the earliest sort of convertible notes was from Cherry Stone Angel Group. So that all in all, about 14.5 million raised, and we're feeling very good about it, and just closed that round this year. So off to the races, right? To start proving out what we promised to do.
Mm-hmm. And where do you see yourself, like, as a company? How big, and what's the ambition? Where do you want to go in 2, 3, 4, 5 years time?
Yeah, 2, 3, 4, 5 years. So So there's a lot of models for 2026 even that people are talking about, which is a 4-year time horizon. There's 2028 targets and 2030 targets. So we want to be designed into at least one or several vehicles by that time. And being able to be the sensor that provides 3D information, high resolution 3D information to the software stack. So anything, there was this plan, say a few years ago, about LiDAR getting into these vehicles in different ways. LiDAR's not panning out the way people thought, but all those same applications are totally open to where we can add benefit.
And what's your licensing model? Is it like subscription based, or do you sell the licenses? How do you, what's the revenue model?
I think that is still as you said, it's a nascent market. People are still trying to figure that out. And it's going to be different for, let's say, L4 trucking than for passenger cars than it is and for robotaxis, right? So there's everything from now for safety critical software, you can't really put it in the cloud and do software as a service and charge per image. So that's kind of off the table. I know that, high speed cell phone companies are trying to sell 5G and say it's reliable, but I think it's folks know that it's not quite close there. So I think there's a lot of clever models from, the easiest one is you sell one and done, but the reality is, my guess is the whole market is going to look a lot more like, cell phones and stuff where you're upgrading software, right? Like these things, software is a bit different in the sense that it's just not static. There's always things you can do better year by year, bug fixes, et cetera, that just make it more secure. Over time, your processor gets upgraded, you have more capability to take advantage of. So, subscription model, maintenance model, there's going to be something that's going to probably, in the long term, resemble more of how things are done for, mobile computing.
Got it. So more subscription maintenance model is going to be the business model in the future in the long term.
Yeah, because it's you have to maintain your software staff to keep improving and checking bugs and adding features and adapting it to different applications. So that's going to drive things into more of subscription-based things. Because if you look at it, right, a car, you expect to have a car for 15 years. Like, it's not a throwaway thing. It's not like you give it, one piece of software, wait for 15 years, and you throw it out to get the new one. Like, you're going to be upgrading it. People are changing their way of looking at products. Products are no longer static. Like, I get it, and it stays the same. No, it's a platform. So I bought the car. It's a platform over which I expect it to improve over 15 years, right? And that's kind of a very different model. And so I expect the software to improve over 15 years, and therefore that model should reflect that. So I think that's kind of the difference between like a more dynamic product and a static product that folks, car used to be more static. You bought it and it was what it was. I don't think that's going to be the case anymore.
Totally. I mean, you need to, the only difference would be between a mobile app store and your services. The lifespan is going to be at least 15 years, right? So you have to keep shipping upgrades, patches, and deal with incidences and many other things. So it's much more complex. The ecosystem may look like the mobile app ecosystem, but it's going to be much more complex in terms of safety and security because we're talking about human lives here. Leif, I have a last question, is that what is your message to our audience? Our audiences are, they're mostly engineers, tech enthusiasts. They're really into the automotive industry, insiders of automotive industry. So what would be your advice to them in terms of, making autonomous vehicles safe and secure? Because that's the title of our podcast, Autonomous Vehicle Safety and Security.
Yeah. So I think my message would be, the core of safety and security is making it accessible to everyone, right? So when you think of new technologies, when you think of new ways of doing things, you're in this optimization space of providing exceptional, exquisite range resolution or angular resolution or whatever it is you're designing. But also have that dimension of like cost and reliability, right? And so how do you make these things accessible for everyone? That's where you're going to get the greatest benefit for society, I think. And being able to get it on every single car, being able to get your tech out there. And there, I spent 12 years building things, $1 million LiDARs, $10 million LiDARs are great. They would have been, we would have had self-driving cars years ago, but it would have cost $100 million, which isn't very helpful to the common person. So I think anything you can do to make your technology more accessible makes it more meaningful, I think. So I think the message is, that's been kind of my push since starting the company. It's like, how do I make this something that anybody can get, not just the luxury cars? And I think that's important to actually give safety to everyone.
That is a very, very amazing message. So safety should be accessible to everyone. It shouldn't be a luxury thing. It should be something that is the basic for every vehicle. I love that. Leif, thank you so much for joining the podcast. It was lovely having you here.
Hey, really nice talking to you, and have a great day.
Yeah. Thank you so much for viewing our podcast or listening to our podcast, depending on in which channel you're watching it. If you have questions, comment, please feel free to write in the comment section, and we'll be more than happy to answer your questions, comments. Thank you so much again for watching. See you in the next episode.